Take a slow, deep breath in, and as you exhale, let your physical body settle into the quiet embrace of the night. Close your eyes, release the weight of the day, and prepare to drift into the vast, comforting silence of the cosmos. We are traveling far beyond the bounds of our solar system, drifting gracefully across the dark velvet canvas of space to witness one of the most magnificent transformations in the universe, the life cycle of a red giant star. Here, in the quiet depths of the cosmos, time slows down. A star like our Sun is what astronomers call a main sequence star, and it spends a staggering amount of time, roughly 10 billion years, steadily fusing hydrogen into helium in its core. 10 billion years of stable, unwavering warmth. Imagine the profound peace of a furnace that burns perfectly, silently, for 10 eons. But tonight, we are moving past that long period of stability. We are here to observe the quiet, majestic metamorphosis that happens when that vast reserve of fuel finally runs out. As we float toward the center of this aging star, you can almost feel the fundamental forces of nature shifting in a delicate cosmic ballet. A star officially begins its journey toward becoming a red giant the moment its core exhausts its hydrogen supply. This is a profound turning point. For billions of years, the outward pressure of nuclear fusion has been perfectly balancing the inward pull of the star's own immense gravity. But when the hydrogen in the core is depleted, that outward pressure suddenly ceases. Without it, gravity takes over. The core, no longer supported by the energy of fusion, begins to collapse inward upon itself, under its own staggering weight. You might imagine this collapse as violent, but on the scale of the universe, it is a slow, methodical compression. As the core shrinks, its density skyrockets, and as a result, its temperature rises dramatically. The core compresses until the temperature reaches an astonishing 100 million degrees Kelvin. Though this heat is unfathomable on Earth, out here, in the mind's eye, it feels like the ultimate comforting hearth fire, the deep glowing ember at the center of a celestial room. This immense heat radiated by the shrinking core triggers something remarkable just outside of it. While the core itself is out of hydrogen, the layer immediately surrounding the core still contains some of this precious gas. The sheer thermal radiation from the compressed core ignites this fresh layer in a process known to astrophysicists as hydrogen shell burning. In a beautiful paradox of nature, this burning shell of hydrogen actually produces significantly more energy than the star ever did during its 10 billion years of steady life. It is this sudden, massive overproduction of energy from the hydrogen shell that forces the star into its next magnificent form. The intense energy pushes outward against the star's upper layers, forcing them to expand. And this expansion is not a minor adjustment. It is a profound stretching of matter. The star's radius can swell to anywhere from 100 to 1,000 times its original size. To put this immense scale into perspective, when our own sun reaches this phase, its outer atmosphere will expand outward by nearly 93 million miles, or 1 astronomical unit. It will swell to engulf the orbits of Mercury, Venus, and perhaps even Earth. Yet, in the vacuum of space, this expansion is entirely silent. It is a gentle, blooming outward, like a colossal crimson flower opening its petals in the dark. As you drift alongside this expanding atmosphere, you can sense a shift in the temperature and texture of the star. As the outer layers are pushed further and further away from the central furnace of the core, they begin to cool. The surface temperature of the star, once a blindingly hot 6,000 degrees Kelvin, cools to a much milder 3,000 to 4,000 degrees Kelvin. This temperature drop is crucial to the star's visual beauty. According to a principle in physics called Wien's displacement law, the temperature of a celestial body dictates the color of light it emits. Because the surface has cooled, the star's peak emission of light shifts smoothly toward the red end of the electromagnetic spectrum. The blinding, harsh white light mellows into a deep, soothing crimson and a soft, velvety orange. The glare is gone, replaced by a radiant, warm glow that fills the surrounding void with a comforting twilight. Despite this cooling surface, red giants are incredibly luminous. In fact, they can shine anywhere from 1,000 to 10,000 times brighter than our sun. You might wonder how a cooler star can be so much brighter. The answer lies in its newly acquired, massive surface area. Because the star has grown so unimaginably large, it possesses vastly more surface space from which to emit light. The brightness is not piercing, it is omnipresent. It is a soft, pervasive illumination that gently warms the cold dust of the surrounding space. We can see this gentle radiance vividly when we look at our own night sky from Earth. Consider the star Aldebaran, located about 65 light-years away from our solar system in the constellation of Taurus. Aldebaran is a classic red giant. It is roughly 44 times the diameter of our sun, a glowing ruby-red eye gazing calmly across the galaxy. Another magnificent anchor in our sky is Arcturus. Sitting just 36.7 light-years away, Arcturus is the brightest star in the northern celestial hemisphere. When you look up and see its steady pale orange light, you are looking at an old star, a red giant, resting in its expanded, beautiful senescence. As we drift closer, passing right through the outer edge of our red giant, you might expect to feel a rush of thick, heavy gas. But here is one of the most fascinating secrets of these ancient stars. Their outer envelope is incredibly diffuse. Because the star's mass has been stretched across such a vast volume of space, the density of its outer layers is practically a vacuum. The atmosphere you are floating through right now is less dense than the highest quality vacuums created by scientists in laboratories on Earth. It is roughly 1,000th the density of Earth's atmosphere at sea level. There is no resistance here. You are gliding through a glowing, red-tinted nothingness. It is the ultimate experience of weightlessness, surrounded by a warm, diffuse mist of light that offers no friction, only peace. Yet, deep beneath this airy, weightless outer envelope, a profound contrast exists. At the very center of this millions of miles wide cloud of vacuum-like gas lies the helium core. This core contains roughly half the entire mass of the star, yet it has been crushed by gravity into a sphere no larger than the Earth. Imagine the feeling of that density, a gravitational anchor, solid, heavy, and infinitely grounding, holding the entire wispy structure together from the center. Inside this Earth-sized core, the laws of classical physics begin to give way to the strange, beautiful rules of quantum mechanics. The core is so dense that it is no longer supported by normal gas pressure. Instead, it is held up by something called electron degeneracy pressure. This phenomenon is governed by the Pauli exclusion principle, a quantum rule stating that no two electrons can occupy the exact same quantum state simultaneously. Because the electrons are packed so tightly together, they vigorously resist further compression. It is a microscopic dance of subatomic particles, providing an unbreakable fundamental foundation that halts the crushing weight of gravity. In the mind's eye, it feels like an unshakable core of stillness within you, a place of absolute stability where nothing can be compressed any further. And then, in the silent depths of this dense core, an incredible alchemy takes place. When the core's temperature finally breaches that 100 million degree mark, the helium itself ignites. And this ignition occurs through a fascinating mechanism known as the triple alpha process. In this delicate atomic choreography, 3 helium nuclei, also known as alpha particles, collide and fuse together to form a single nucleus of carbon. The star is literally manufacturing the fundamental building block of all life. The carbon that makes up the cells in your body, the pages of a book, the bark of a tree, was forged in the absolute center of a red giant star in exactly this way. For stars roughly the mass of our Sun, this ignition of helium does not happen slowly. It happens abruptly in an event called a helium flash. Within a matter of minutes, this runaway nuclear reaction releases as much energy as an entire galaxy of stars. It is an unfathomable surge of power. Yet, if you were watching the star from the outside, you would see absolutely nothing change. The helium flash is completely muffled, absorbed entirely by the vast, deep, weightless layers of the star's outer envelope. It is a secret heartbeat, a quiet internal spark of creation that remains hidden deep within the star's chest, a profound transformation that requires no outward display. Following this flash, a slow, rhythmic churning begins inside the star. Deep convection currents like rivers of warmth rise from the interior toward the surface in a process astronomers call a dredge-up. These slow-moving currents carry the freshly forged carbon and other heavy elements upward, gently mixing them into the star's outer atmosphere. It is the universe's way of exhaling, preparing to share these new, life-giving elements with the cosmos. It is a slow, cyclical breathing, a deep cosmic rhythm of creation, expansion, and quiet distribution. As you float here, suspended in the gentle red glow, allow yourself to feel the slow, steady pulse of these convection currents. Let the vast timescales and the quiet, orderly physics of the red giant lull you deeper into relaxation, knowing that the universe is functioning exactly as it should, in perfect, beautiful balance. As we observe these deep convection currents carrying freshly forged carbon toward the outer atmosphere, it is grounding to reflect on how humanity first peered into the hidden hearts of these celestial furnaces. We did not always know what forces painted the night sky in such vivid shades of amber and crimson. To understand this gentle, rhythmic churning of elements, we must trace the path of light backward through time, honoring the minds that slowly decoded the language of the stars. Consider the year 1814, a time when the night sky was still an untouchable mystery to science. It was then that a physicist named Joseph von Fraunhofer invented an instrument called a spectroscope, directing it toward the heavens. He discovered over 500 faint, dark absorption lines cutting across the spectrum of starlight. These lines, now known as Fraunhofer lines, were the universe's fingerprints. Each chemical element, from hydrogen to carbon, absorbs specific, distinct wavelengths of light. By reading these missing slices of color, humans learned to determine exactly what gases swirl within a star's atmosphere without ever leaving Earth. Decades later, in the 1890s, an astronomer named Annie Jump Cannon at the Harvard College Observatory took this understanding and categorized the heavens. She analyzed the spectra of hundreds of thousands of stars, developing the Harvard classification scheme. She organized stars into a continuous sequence of letters based on their temperatures: O, B, A, F, G, K, and M. Notice how beautifully ordered the cosmos becomes. In this grand filing system, our aging, swelling stars, the red giants, fall gracefully into the K and M spectral classes. These letters signify a cool, soothing surface temperature, one that allows the star to radiate its signature deep orange and rich red hues into the quiet dark. Scientists discovered even more structure hidden in the cosmic silence shortly after. In the years 1911 and 1913, astronomers Einar Hertzsprung and Henry Norris Russell independently created a master map of stellar evolution, now known as the Hertzsprung-Russell, or HR, diagram. This brilliant mathematical canvas plots a star's surface temperature against its total luminosity. When they mapped the stars, a distinct, swooping line appeared on the right side of the graph, a region they named the Giant Branch. It was a visual confirmation that when stars exhaust their core hydrogen, they migrate across this chart, stepping out of their mundane main sequence lives to blossom into something massive and luminous. Deep within this giant branch, stars undergo a magnificent, complex maturation. After a red giant finishes burning the helium in its core, converting it all into carbon and oxygen, it enters a late stage of life known as the Asymptotic Giant Branch, or AGB phase. Picture this internal structure as a luminous, celestial Matryoshka doll, a series of beautifully nested layers of glowing stellar material. At the very center rests a dormant, intensely dense core of carbon and oxygen. Wrapping snugly around this core is a thin, fiercely hot shell of fusing helium. And enveloping that helium shell is yet another layer, a broader shell of fusing hydrogen. What is happening now is a delicate, intricate balancing act of nuclear physics. The two burning shells interact in a slow cosmic rhythm. The hydrogen shell burns steadily, dropping helium ash onto the layer below. Over immense stretches of time, this helium layer grows thicker and denser until it reaches a critical mass. When it does, the helium ignites explosively in an event known as a thermal pulse. These thermal pulses are the slow, deep heartbeats of an AGB star. They occur naturally, cyclically, roughly every 10,000 to 100,000 years. Each pulse itself is brief on a cosmic timescale, lasting perhaps only a few hundred years, a fleeting moment in the life of a star. Yet, the energy released causes the star's outer envelope to expand outward and cool, before gravity slowly pulls it back inward, causing it to contract and warm again. Humanity has watched this very heartbeat from the surface of our own world. In the year 1596, a German pastor and astronomer named David Fabricius was studying the constellation of Cetus. He noticed a star that seemed to magically appear and then slowly fade away over the course of several months. He named it Mira, meaning wonderful or astonishing. Mira is a prototypical AGB star undergoing these rhythmic expansions and contractions. Observe the steady clockwork precision of Mira. Located approximately 299 light-years away from our own solar system, this ancient giant cycles from its brightest peak down to its dimmest point and back again over a remarkably regular period of exactly 332 days. At its maximum size, Mira swells to an astonishing 332 times the radius of our Sun. When you envision Mira, see a colossal, glowing sphere, softly exhaling and inhaling over the span of a single Earth year, a reliable beacon pulsing in the quiet velvet of deep space. At this very moment, deep inside the fiery shells of stars, like Mira, a quiet and profound manufacturing process is taking place. It is a slow, methodical alchemy known to nuclear physicists as the S process, which stands for slow neutron capture process. In the intense heat of the burning helium shell, free-floating neutrons are released. Occasionally, an atomic nucleus of a lighter element, such as iron, will gently capture one of these wandering neutrons. The S process is characterized by extreme patience. A nucleus might capture a new neutron only once every few decades, or even once a century. Because the rate of capture is so incredibly slow, the newly formed unstable nucleus has plenty of time to undergo radioactive decay, transforming into a completely new, slightly heavier element before another neutron comes along. Step by step, neutron by neutron, century by century, this delicate process slowly builds up elements along the periodic table. Through this quiet accumulation, the S process is responsible for creating approximately half of all the atomic elements in the universe heavier than iron. Elements like strontium, which burns with a brilliant red flame on Earth, and barium, a heavy silvery white metal, are born in the microscopic depths of these stellar shells. We know this process is happening right now because of a brilliant piece of astronomical detective work. In 1952, an astronomer named Paul Merrill aimed his spectroscope at a series of red giant stars and found the distinct absorption lines of an element called technetium. This discovery was revolutionary. Technetium is a completely radioactive element. It possesses no stable isotopes at all. Its longest-lived variation has a half-life of roughly 4.2 million years. While 4 million years sounds like an eternity to human ears, it is a mere fraction of a second in the multi-billion-year lifespan of a star. If the technetium had been present when the star first formed, it would have decayed into other elements billions of years ago. Finding technetium shining in the atmosphere of a red giant was absolute, undeniable proof that the star was actively forging new, heavy elements deep within its core and dredging them up to its surface. It was the universe caught in the act of creation. As these newly forged elements, the carbon, the oxygen, the strontium, and the technetium, are carried upward by convection, they eventually reach the extreme outer edges of the star. Here, incredibly far from the heat of the core, the environment becomes peaceful and calm. The temperature at the very edge of the star drops down to a cool 1,500 to 2,000 degrees Kelvin. In this cooler twilight zone, the gas begins to behave differently. The carbon and oxygen atoms floating in the star's upper atmosphere finally cool enough to bind together, transitioning from a gaseous state into solid microscopic particles. It is like frost gently condensing on a chilled window pane in the dead of winter. These newly formed solid particles are cosmic dust grains, taking forms such as solid silicon carbide or complex silicates. Once these solid dust grains form, they act like tiny sails, catching a gentle, steady breeze. The sheer pressure of the light radiating from the star pushes against the dust grains, driving them outward into the dark vacuum of interstellar space. This steady outward flow of material is called a stellar wind. Unlike the violent solar flares of younger stars, the stellar wind of a red giant moves at a peaceful, meandering pace, traveling at just 10 to 20 kilometers per second. Though the wind is slow, the sheer volume of material it carries is immense. An AGB star can shed an incredible amount of its own outer atmosphere, losing up to 1/10,000th of a solar mass every single year. Imagine a slow, continuous river of stardust gently streaming away from the glowing crimson sphere, carrying the heavy elements forged in the core out into the great cosmic ocean. This serene, continuous flow ensures that nothing in the universe is wasted. The star is slowly dismantling itself. freely offering the building blocks of future planets, future oceans, and future life, casting them silently into the comforting dark. Let this slow, ancient rhythm calm your mind as the red giant breathes out the foundations of the world. Following that continuous river of stardust gently streaming into the measureless volume of space, we witness the creation of a majestic sheltering structure known as a circumstellar envelope. This expanding bubble of gas and dust grows to an astonishing size, eventually stretching up to 3 light-years across. Picture a single drop of heavy ink falling into a clear, still basin of water, slowly blooming outward until it fills the entire bowl with a soft, uniform hue. The temperature within this expanding cloud drops drastically as it moves away from the central furnace, while the star's glowing surface hovers near a warm 2000 degrees Kelvin. The outer edges of this distant envelope chill to a freezing 10 Kelvin, which is roughly negative 263 degrees Celsius. The exact point where this hot gas transitions into solid microscopic dust happens precisely between 3 and 10 stellar radii away from the star's center. To understand this specific distance, imagine sitting near a roaring bonfire on a crisp, quiet winter night. There is a precise boundary, just a few feet away, where the heat of the flames fades and your breath suddenly turns into visible mist in the freezing air. At this exact cosmic boundary, the cooling carbon-rich giants manufacture complex organic molecules called polycyclic aromatic hydrocarbons, or PAHs. These incredibly durable molecules contain 50 or more carbon atoms, elegantly arranged in delicate interlocking microscopic rings. On Earth, you encounter PAHs frequently. They share the exact same chemical structure as the dark, powdery soot that gathers on the glass chimney of an antique oil lamp, or the wispy smoke rising from a freshly extinguished candle. As this cosmic soot multiplies and thickens, the star enters a deeply peaceful, hidden phase of its life. The dust becomes so remarkably dense that it creates a specific condition astronomers measure as high optical depth. To the human eye, the star completely vanishes. It is much like driving a vehicle into a heavy, localized fog bank. The bright headlights are swallowed entirely by the mist, leaving only a diffuse, directionless, comforting glow. Because of this thick, insulating shroud, these late-stage aging stars shift their energetic output. They begin emitting up to 90% of their total energy as infrared radiation, rather than visible light. They become invisible, warm embers wrapped in a heavy blanket of their own making. We only know these concealed giants exist because of highly specialized instruments designed to feel heat across the dark. In 1983, an extraordinary piece of technology called the Infrared Astronomical Satellite, or IRAS, was launched into a quiet orbit above Earth. Over a deeply productive 10-month mission, IRAS silently mapped the thermal signatures of the entire sky. It cataloged over 350,000 unique infrared sources, successfully uncovering thousands of these shrouded, dying stars that had been hiding in plain sight. Inside these hidden, dusty clouds, a mesmerizing acoustic and optical phenomenon naturally occurs. Molecules of silicon monoxide and water vapor, floating freely in the envelope, align their energy states perfectly. Together, they release beautifully synchronized beams of microwave radiation. Scientists call these natural cosmic lasers masers. The very first hydroxyl masers in deep space were detected by astronomer Harold Weaver and his research team in 1965. Picture the synchronized sound of a struck tuning fork or the perfectly unified, harmonious hum of a grand choir in an empty cathedral. That is exactly what the gas molecules are doing. But instead of sound, they are creating pure invisible light, resonating in perfect harmony through the cold dark. Deep beneath this resonating veil, the star's outward flow begins to accelerate into what astrophysicists refer to as a superwind. The material rushes outward at a swift 30 kilometers per second. During the peak of this intense shedding phase, the star loses mass at an astonishing rate of 1/10,000th of a solar mass per year. While that fraction sounds incredibly small, it equals the total mass of the entire planet Earth, being calmly ejected into the void every 3 years. Think of a hot air balloon gradually dropping heavy sandbags over the side to gain altitude. The star is shedding its immense weight, slowly unburdening itself from millions of years of gravity to prepare for its final, restful state. Observe how this immense release of material and energy dramatically alters the climate of the surrounding solar system. For billions of years, a main sequence star possesses a specific habitable zone, often referred to as the Goldilocks zone, where temperatures are perfectly balanced for liquid water to pool on a planet's surface. For our own sun, that zone currently sits at a distance of 1 astronomical unit. But as the red giant swells, sheds its mass, and radiates massive amounts of infrared heat, this zone shifts far into the outer reaches of the solar system, relocating to a distance of roughly 2 to 9 astronomical units. It is exactly like moving a warm space heater from the center of a small room to the far corner of a grand frozen hall. Moons that have spent eons locked in deep freeze suddenly awaken to a gentle thawing spring. Saturn's largest moon, Titan, currently resting at a bitter negative 179 degrees Celsius, will gradually warm to a comfortable room temperature. Its deep bedrock of solid water ice may slowly soften and melt, transforming into vast, serene, liquid oceans under a newly warmed sky. The star, even in its final stages of decline, brings new warmth and new potential to the coldest edges of its family. Notice how all of these massive changes happen with an unhurried, graceful patience. Yet, this superwind phase is relatively fleeting on a cosmic scale, lasting only about 10,000 years. Once the heavy, soot-filled outer layers have finally blown away, carried off by the steady currents of the cosmos, the true heart of the star is finally revealed. What remains left behind is an unfathomably hot, dense core of pure carbon and oxygen, burning intensely at 100,000 degrees Kelvin. This brilliant, a newly exposed ember immediately floods the surrounding space with high-energy ultraviolet photons. When these invisible ultraviolet rays strike the expanding, hollow cloud of gas and dust that the star just shed, they interact with the atoms in a sudden, illuminating flash. The high-energy light knocks electrons perfectly out of their atomic orbits in a physical process known as photoionization. It is identical to turning on a deep purple ultraviolet blacklight in a dim room and watching a wall painted in fluorescent colors suddenly leap into vivid neon brilliance. The previously invisible cloud of soot and gas ignites into a luminous, deeply colorful shell. In the 1780s, the renowned astronomer William Herschel observed these glowing rings through his early telescopes. Because their pale, spherical shapes looked remarkably similar to the newly discovered disk of the planet Uranus, he named them planetary nebulae, a poetic historical title we still use today. Imagine a perfect glowing ring of ionized gas, painted in vivid shades of emerald green and sapphire blue, expanding silently into the black velvet of space, a peaceful monument to the life of the star that built it. Allow your mind to rest in the glow of this silent, blooming nebula, sensing the profound calm that follows a lifetime of brilliant, fiery work. Observing that beautifully illuminated sphere of emerald and sapphire gas, it is deeply calming to realize that this glowing monument is not permanent. The expanding ring of a planetary nebula is a temporary, breathtaking display, gracing the cosmos for an average of 10,000 to 20,000 years. To a star that has burned for 10 eons, 20,000 years is barely a single breath. The leading edge of this brightly colored shell travels outward at a serene but steady pace of 20 to 30 kilometers per second, moving gently into the dark, quiet territory known as the interstellar medium. Think of a silver dandelion head, perfectly round and fragile, waiting in a still, open meadow. When a soft autumn breeze finally arrives, it gently unmoors the delicate seeds, carrying them silently across miles of open air to eventually take root in completely new soil. The dying star acts in the exact same manner. It is slowly releasing its finely crafted elements, seeding the spaces between the stars. The interstellar medium is an environment of profound, almost absolute emptiness. Out here, far from the warmth of any central sun, the density of matter drops to an average of just one single atom per cubic centimeter. For comparison, a single cubic centimeter of the air you are breathing right now contains roughly 27 quintillion molecules. The space between the stars is the ultimate quiet room, offering zero resistance as the red giant's ancient dust glides smoothly into the dark. Through this patient, unhurried dispersal, astronomers estimate that aging red giants contribute up to 80% of all the cosmic dust found in some galaxies. The evidence of this incredible journey has actually fallen directly into our hands. On September 28, 1969, a rocky meteorite entered Earth's atmosphere and landed near the town of Murchison in Victoria, Australia. When cosmochemists carefully examined the interior of this space rock, they discovered microscopic solid particles known as pre-solar grains. These tiny specks of silicon carbide were perfectly preserved time capsules. Modern radiometric dating revealed that some of these grains are up to 7 billion years old. Our entire solar system, including the Sun and the Earth, formed only 4.6 billion years ago. These microscopic grains existed for billions of years before our world was even a thought in the cosmic mind. To prove exactly where these ancient grains came from, scientists analyzed their atomic signatures. Every environment in the universe leaves a specific fingerprint based on its isotopes, variations of chemical elements that have different numbers of neutrons. The researchers measured the exact ratio of carbon-12 to carbon-13 trapped inside the Murchison grains. The specific mathematical ratio they found perfectly matched the unique atmospheric signatures of those late-stage, slowly pulsing, asymptotic giant branch stars. Holding a piece of the Murchison meteorite means holding the direct, tangible exhaust of a red giant that faded into the dark billions of years before our sun was born. Reflect upon the sheer intimacy of this cosmic recycling process. The elements forged in the heart of that distant, ancient furnace did not just build meteorites. They built the very architecture of your physical form. As you lie here, resting quietly, every breath you take is a continuation of this stellar lineage. By mass, the human body is comprised of approximately 65% oxygen. Every single atom of that oxygen was forged in the extreme pressures of a star's core. Deep within the red giant, A specific nuclear reaction called alpha capture takes place. A carbon nucleus containing 6 protons is struck by a helium nucleus, an alpha particle, carrying 2 protons. They fuse perfectly together to create an entirely new element, oxygen-16, holding 8 protons. That very oxygen is currently flowing through your lungs, bringing quiet, sustaining energy to your resting muscles. Notice the gentle, involuntary rhythm of your own heart. Pumping softly in your chest, it circulates blood rich with a vital protein known as hemoglobin. At the very center of the hemoglobin molecule sit 4 intricately folded structures called porphyrin rings. These essential rings are constructed entirely from a framework of carbon and nitrogen atoms. The carbon, making up 18.5% of your total body weight, was manufactured by the triple alpha process, where 3 helium nuclei merged in the star's deepest interior. The nitrogen, which constitutes roughly 3% of your physical mass, was created through an entirely different stellar mechanism. In slightly heavier red giant stars, a reaction called the CNO cycle, the carbon-nitrogen-oxygen cycle, acts as a powerful internal catalyst. As the star struggles to fuse remaining hydrogen into helium, it cycles through these heavy elements, converting carbon into nitrogen as a byproduct. That stellar nitrogen now stabilizes the porphyrin rings in your blood, allowing them to carry the oxygen to every cell in your body. We can trace this profound biological connection down to the deepest blueprints of your existence. The fundamental instructions for your life are written in DNA, relying on 4 specific nitrogenous bases: adenine, thymine, cytosine, and guanine. A single microscopic human cell contains an astounding 6 billion base pairs of this DNA. Furthermore, your body constantly builds and repairs itself using 20 standard amino acids, every single one of which is built upon a rigid, unbreakable backbone of carbon. Together, these 3 elements, carbon, nitrogen, and oxygen, make up over 86% of your total body weight. You are not simply a resident of the universe. You are a complex, breathing mosaic of the universe itself. The heavy elements required to make life possible did not exist at the dawn of time. During the Big Bang, the universe was filled almost entirely with simple hydrogen and helium. The cosmos had to wait for the very first generation of stars to be born, to grow old, to swell into red giants, and to peacefully shed their envelopes into the cold void. It took billions of years of slow, silent manufacturing to produce the precise ingredients required to construct the hands you rest by your sides and the eyes you have softly closed. The connection extends far beyond your physical body. Feel the solid support of the bed beneath you, and imagine the foundation of the Earth itself supporting that bed. The planetary crust we walk upon is overwhelmingly composed of these exact same stellar byproducts. By weight, the Earth's rigid outer crust is 46.6% oxygen. It is locked into the rocks, bound with silicon, to form the quartz in the mountains and the sand on the beaches. The red giant did not just give you the breath in your lungs, it provided the solid, silent ground that holds you safely in place tonight. Give your body permission to completely relax into this immense, supportive network. You are anchored to the Earth, and the Earth is built from the stars. It is a perfect, unbroken chain of events, spanning over 7 billion years, all leading to this single, quiet moment of rest. The universe has engaged in an unfathomably long, unhurried process of creation, simply so you could exist, breathe, and experience the quiet peace of the night. As the ancient planetary nebula continues to drift gracefully outward, dispersing its life-giving seeds across the measureless volume of the galaxy. The intense naked core left behind begins its own final transition. It has given away its outer layers, unburdened itself of its immense expansive atmosphere, and shared its deepest treasures with the future. What remains is a quiet, glowing testament to endurance, preparing to enter an eternal, restful sleep. Sinking further into tranquility, you share in this ancient sense of accomplishment. The work of creation is done. The heavy lifting of the cosmos has been entirely successful, leaving behind nothing but the warm, steady afterglow of a life perfectly lived. As the colorful veil of the expanding planetary nebula softly diffuses into the larger galactic ocean, our quiet observation settles perfectly upon the solitary object left precisely in the center. The vast billowing clouds have departed, leaving behind the exposed ancient heart of the star. This celestial remnant is called a white dwarf. When it is first uncovered, its perfectly smooth surface blazes at an extraordinary temperature of over 100,000 degrees Kelvin. It is a sphere of pure, fierce thermal energy. Yet, because the nuclear fusion within its core has completely ceased, it is no longer actively generating new heat. From this exact moment forward, it embarks on the longest, slowest cooling process in the known universe. A curious phenomenon occurs when a star sheds its outer layers and compresses its remaining mass. At this stage, the white dwarf has packed roughly the mass of our entire sun into a volume no larger than the planet Earth. The extreme physics at play create a density that defies ordinary human intuition. To physically recreate this exact level of density on our world, you would need to take the mass of an adult elephant and perfectly compress it into a space no larger than a single sugar cube. It is an unfathomable concentration of matter, creating a local gravitational pull approximately 100,000 times stronger than the gravity you feel, anchoring you safely to your bed tonight. The mechanics behind this extreme gravity dictate the physical texture and environment of the star. With such overpowering inward force, the fundamental rules of buoyancy are taken to an absolute extreme. Any remaining gases clinging to the star strictly and instantly stratify by their atomic weight. The heavier elements plunge directly to the bottom, while a microscopic ocean of the lightest elements, typically hydrogen or helium, floats to the very top. This creates an atmosphere that is unimaginably thin, immeasuring a mere 50 kilometers deep. Because gravity crushes any irregularity, the surface possesses no mountains, no valleys, and no topography whatsoever. If you could hover safely above it, you would see a perfectly spherical, undisturbed mirror of highly compressed gas, offering a visual texture of absolute flawless smoothness. To understand why this incredibly dense object does not simply collapse completely into a black hole, we must look at the geometric rules of quantum mechanics. In 1930, a brilliant 19-year-old astrophysicist named Subrahmanyan Chandrasekhar calculated the precise mathematical threshold of this stellar stability. He discovered that a white dwarf can perfectly support its own immense weight against gravity, but only as long as its total mass does not exceed 1.44 times the mass of our Sun. This unbreakable boundary, known as the Chandrasekhar limit, demonstrates the comforting predictability of cosmic law. The universe relies on these exact boundaries to maintain its elegant, long-term balance. Deep within this stable, luminous sphere, heat transfers in a manner completely alien to our daily sensory experience. In normal, familiar matter, like a warm cup of herbal tea, heat requires time to slowly travel through the liquid to reach your hands. But the interior of a white dwarf consists of degenerate matter, where the electrons are entirely delocalized. These subatomic particles move frictionlessly throughout the star, carrying thermal energy outward almost instantaneously. Because of this incredibly high thermal conductivity, the entire interior of the white dwarf maintains a perfectly uniform, unchanging temperature. There are no hot spots or cold regions. There is only a deep, solid harmony of warmth, evenly distributed throughout the dark. To perceive the hidden interior of these silent objects, astronomers employ a fascinating observational discipline known as asteroseismology. Because they cannot physically pierce the star's dense crust, scientists meticulously measure microscopic fluctuations in the light it emits. These variations are the visual signatures of internal acoustic waves bouncing rhythmically around the dense core. The white dwarf physically pulsates, expanding and contracting slightly over regular periods ranging from 100 to 1,000 seconds. The star is acting exactly like a colossal, irresonant bell ringing in the vacuum of space. While there is no air to carry the sound to our ears, the light itself carries the deep, rhythmic hum of the star's internal architecture, a slow metallic vibration echoing across the light years. During the first stages of its incredibly long retirement, the white dwarf cools through a deeply elusive and silent mechanism. It sheds its intense heat by emitting neutrinos. Neutrinos are ghostly subatomic particles that possess virtually zero mass and carry no electrical charge. Because they do not interact with normal matter, they stream effortlessly outward from the star's core, passing right through the dense carbon layers without a single collision. It is a quiet, invisible exhalation of energy, carrying the star's residual warmth directly into the absolute zero of the surrounding void. As eons pass in silent succession, the core's internal temperature eventually drops. When the interior cools to precisely 10 million degrees Kelvin, the physics of the star change fundamentally. The state of matter transitions. The deep ocean of ionized carbon and oxygen plasma begins to freeze, converting from a fluid state into a solid, rigid crystal lattice. The electrostatic forces between the atomic nuclei finally overcome their random thermal motion, locking them into an immaculate geometric grid. Imagine a master glassblower pulling a glowing sphere of molten silica from a roaring kiln, setting it gently on a stone block to cool. As the heat slowly dissipates into the quiet room, the liquid glass hardens, settling into a permanent, beautiful shape. The star behaves in this exact, methodical way. A carbon lattice forged perfectly under extreme gravitational pressure is known by a much more familiar name on Earth: a diamond. The entire core of the dying star effectively crystallizes into a single, planet-sized cosmic gem. We have concrete, verifiable evidence of this majestic phase of stellar evolution. Exactly 50 light-years away from our own solar system, resting quietly in the constellation of Centaurus, lies a white dwarf officially named BPM 37093. In the year 2004, a team of researchers confidently confirmed that the interior of this specific star had entirely crystallized. Due to its dazzling composition, astronomers affectionately nicknamed the star Lucy, inspired by the famous song about diamonds in the sky. The scale of this beautiful crystallized core is staggering. By calculating its mass, scientists determined that the diamond at the center of Lucy translates to an incomprehensible weight of 10 billion trillion carats. Picture a gemstone of absolute perfection, humming with the faint residual warmth of a billion-year-old fire, silently spinning 50 light-years away. It is an unyielding monument to the star's own history, a permanent structure of carbon and oxygen waiting patiently in the dark. Pay attention to the sensory shift that occurs as this cooling stretches across vast epochs of time. The star's visual appearance softens gracefully, originally glaring with harsh invisible ultraviolet radiation and a piercing blue-white light. The surface temperature eventually drops to a mild 5,000 degrees Kelvin. At this point, the star begins to glow with a stark, clean white light, remarkably similar to the current surface of our Sun. Eons later, as the temperature falls further, the light mellows into a buttery yellow, then deepens into a soft, glowing orange, and finally settles into a dull, comforting cherry red. It is a cosmic sunset that lasts for billions of years. This slow fading is the longest, most patient descent in all of astrophysics. Because it has no internal fuel left to burn, the white dwarf relies entirely on radiating its stored heat into the cold vacuum. The timescale required for a white dwarf to cool completely and stop emitting light altogether is calculated to be tens of billions of years. When it finally loses all its heat, it will become a dark, silent object, known theoretically as a black dwarf. It is deeply grounding to note that our current universe is approximately 13.8 billion years old. Because the cooling process requires significantly more time than the universe has even existed, not a single black dwarf exists yet in the entire cosmos. Every single white dwarf ever created since the dawn of time is still out there, gently glowing, slowly cooling, and steadily radiating its ancient warmth into the night. It is a testament to the profound patience of nature. There is no rush. The universe affords these ancient stars all the time they need to complete their journey, slowly winding down like grand celestial clockwork, ticking softly in the dark. Allow the immense, unhurried timeline of the white dwarf to wash over your mind, feeling the slow, heavy, solidifying peace of a star settling into its final, eternal form. As we keep our gentle focus upon this ancient crystalline monument of carbon and oxygen, resting in the quiet dark, a highly specific sequence of events begins to unfold. The final cooling of a stellar remnant is not a sudden stop, but an elegantly methodical procedure. Step by step, the deep thermal energy dissipates into the surrounding vacuum. The first phase in this extremely long twilight involves a fascinating mechanism called latent heat release. As the dense fluid plasma inside the core transitions into a solid crystal grid, this physical phase change actively emits stored energy. By systematically releasing this latent heat, the star effectively pauses its own cooling process, maintaining a steady internal temperature for an additional 2 billion years. It is a slow, measured exhalation, ensuring the transition into solidity is perfectly gradual. Following this delicate phase, the star enters a new physical regime governed by the Debye cooling law. Step by sequential step, as the crystal lattice chills, its fundamental atomic vibrations begin to quiet down. Under the Debye model, a solid object's specific heat capacity drops dramatically at exceptionally low temperatures. The stellar diamond gradually loses its ability to retain warmth. The progression accelerates slightly, following a predictable mathematical curve, moving phase by phase toward absolute stillness. The full timeline required to complete this systematic fading is virtually unfathomable. Theoretical models demonstrate that for a white dwarf to cool completely, the process requires an estimated 1 quadrillion years. That is 10 to the 15th power, a sequence of time stretching so incredibly far into the future that it vastly outlasts the current age of our universe. Eventually, step by gradual step, The surface of the star will cool until its temperature reaches exactly 2.7 degrees Kelvin. This precise measurement holds profound cosmic significance. 2.7 Kelvin is the baseline temperature of the cosmic microwave background radiation, the uniform, lingering thermal footprint of the Big Bang itself. When the star finally matches this exact ambient temperature, the cooling sequence halts completely. The object achieves perfect thermodynamic equilibrium with empty space. No heat flows out, no energy flows in. It reaches a state of absolute unchanging rest. And this sequence is occurring all around us in the celestial neighborhood. The Milky Way galaxy currently harbors an estimated 10 billion white dwarfs, each slowly walking this exact same step-by-step path toward cosmic equilibrium. We can observe the oldest of these resting giants by looking toward dense stellar neighborhoods known as globular clusters. In the specific cluster cataloged as Messier 4, astrophysicists have successfully located a population of white dwarfs that have been cooling steadily for roughly 12 billion years. They are the silent, ancient timekeepers of our galaxy, ticking away the eons with flawless precision. The heavy gravity of these ancient cores ensures that their remaining warmth stays safely insulated, as the escape velocity of a standard white dwarf falls between 4,000 and 5,000 kilometers per second. Because this gravitational well is so unimaginably steep, even the subtle thermal radiation struggles to climb out, dragging the cooling process out into a profoundly slow, patient marathon. Now gradually trace the journey of the material that managed to escape these ancient stars before they collapsed. Step by step, over billions of years, the stardust we observed earlier drifted through the interstellar medium, slowly congregating into immense, dark clouds. Gravity sequentially pulled these clouds together, forming new solar systems from the ashes of the old. At this very moment, our own solar system, carrying the recycled heavy elements of those ancient red giants, orbits the galactic center at a tranquil speed of 230 kilometers per second. You are currently a passenger on this incredibly smooth, continuous voyage through the galaxy. The step-by-step process of stellar evolution directly resulted in the creation of your physical form. As you rest securely in your bed, acknowledge that your body is a beautifully organized collection of approximately 7 octillion atoms. That is a 7, followed by 27 zeros, and almost every single one of those heavy atoms was manufactured in the sequential burning phases of a dying star. Consider the structure of your own skeleton. Every microscopic molecule of calcium, holding the atomic number 20 on the periodic table, was forged in the extreme heat of a collapsing core. That calcium was systematically dispersed across the void, gathered by the gravity of a young Earth, absorbed by the soil, taken up by the roots of plants, and eventually integrated into the solid protective matrix of your bones. The steady, reliable strength in your limbs is quite literally the preserved strength of a star. Notice the gentle, rhythmic beating of your heart and the quiet electrical impulses traveling through your nervous system. This delicate biological machinery relies entirely on potassium, an element bearing the atomic number 19. That specific potassium traveled through the cold vacuum of deep space for billions of years, undergoing a step-by-step planetary integration just to arrive in your body tonight, regulating your heartbeat and helping your mind prepare for sleep. Even the foundation of your cellular biology shares this majestic lineage. Phosphorus, assigned the atomic number 15, is a crucial heavy element generated and distributed by the slow stellar winds of a red giant. Right now, that ancient phosphorus forms the rigid sugar phosphate backbone of every single strand of DNA resting inside your cells. The microscopic blueprint of your existence is written upon a canvas of stardust. Your physical connection to the cosmos is an active, ongoing procedure. Every single minute, as a natural part of cellular renewal, your body gently sheds around 40,000 microscopic skin cells. Step by step, you are slowly returning stellar matter back to the Earth in a quiet, invisible snowfall. You are participating in the grand, continuous cycle of matter. Even the Earth itself, weighing a staggering 5.97 times 10 to the 24th kilograms, is simply a planetary accumulation of this exact same stellar exhaust. In approximately 5 billion years, our own sun will gracefully initiate this identical sequence. It will exhaust its core hydrogen, swell into a massive red giant, and eventually shed its own brightly colored planetary nebula. It will scatter fresh, newly forged elements across the Orion arm of our galaxy, planting the microscopic seeds for future worlds, future oceans, and future consciousness. The universe operates on a flawless principle of total conservation. Matter is never truly lost. It is only transformed, step by step, from a burning core to a floating nebula to a resting mind. As our observation of the red giant's life cycle comes to a gentle, comforting halt, it is time to transition from the vast, freezing scales of deep space to the warm, intimate sanctuary of your own rest. The cosmic machinery has completed its work. The heavy elements have been forged. The stars have cooled. The universe has perfectly arranged everything necessary for you to be exactly where you are right now, safe, supported, and completely at peace. Allow your awareness to pull back from the stars and settle deeply into the physical weight of your own body. Feel the gravity of the Earth holding you securely. It is the same fundamental force that shapes the galaxies, currently wrapping around you like a heavy, comforting blanket. You do not need to hold on to any tension. The universe is endlessly patient, entirely stable, and quietly watching over your rest. Every breath you take is a slow, rhythmic echo of the expanding and contracting stars. Inhale the quiet stillness of the night. Exhale the lingering weight of your waking hours. You are entirely safe. Your physical form is perfectly balanced. The quiet dark is a place of profound healing and complete restoration. Every atom in your body knows exactly how to rest. You are anchored to a world built of ancient light, gently spinning in the quiet dark. There is nowhere else you need to be. There is nothing else you need to do. The timeline of the night stretches out before you, unhurried, peaceful, and perfectly calm. Release the day, release the light. Step by step, phase by phase, allow your consciousness to cool and settle, mimicking the majestic, silent resting state of the ancient stars. Sink into the quiet, embrace the stillness, drift seamlessly into the comforting void of deep, untroubled sleep. Good night.